is. So this is again from that online text that I referred you to. And I mentioned before that this is really our goal. And maybe I will go ahead and chat with somebody. So how about Ryan? Are you here? Ryan Barnhart.
Yeah, I'm here.
Hi, Ryan. How you doing this morning?
I'm good. How are you?
Pretty good, pretty good. So Ryan, you see this top graph? It has a consumer choice problem illustrated,
Yeah.
and actually, I think it's kind of poorly illustrated, but it's clear. I'll tell you why it's poorly illustrated in a little bit. But you see where it says PCC. That stands for what they call the price consumption curve. I prefer price expansion path, but that's okay. But this green line shows a series of equilibria for the consumer choice problem as the price of the good on the x-axis changes. Um, and here just two of them are illustrated, but the whole green line is for a potentially infinite number as you're changing the price by like pennies, and slowly this blue line, which is the and I don't know, can you see my cursor when I move along, or no, you can't see my cursor?
Yeah, we can.
Okay, yeah. So these blue lines are the budget lines, and as the blue line was slowly to rotate out as we lower the price of the good on the x-axis, then this would be all of, and I don't know if you're familiar with this language, but I'm just going to use it because it's correct, and that is whenever you have a graph, you can refer to it as a locus of points. So this green locus is all of those consumption bundles the consumer would consume as the price of X changes. Okay, are you following me, Ryan?
Yeah.
Now, notice there's this green line down here, which is the demand curve. Okay, and it's the price of good X. So implicitly, as we change the price of X, the budget constraint or the budget line is rotating out, okay? And the consumer's choosing different consumption bundles, and the consumption bundles have the quantity of good X and of good Y. So the consumer's choosing to consume as the price of X changes.
Mm-hmm.
So what that means is we actually can extract from the consumer choice problem all of the information we need to plot the demand curve for X. So as we change the price of X, now we're moving along the vertical axis here. And instead of each consumption bundle has a quantity of X and a quantity of Y, we're just looking at the quantity of X alone. And if we plot the price of X against the quantity of X, then we get the demand curve for X. And at this point, I want to say, voila, you know.
Yeah.
And the main point is that is that the consumer choice problem answers the question for us in detail. Where does demand come from? And is that clear?
Yes, it is.
Yeah, so because I mean, if you thought about it, Ryan, I don't know if you have, but it's totally okay if you have or you haven't. But intuitively, you just kind of magically, right? You see the demand curve at different prices, different quantities of X are purchased. And normally we would just see a market level demand curve. And remember, the market demand curve is an aggregation. It's an adding up of individual demand curves. But if I wanted to get Ryan's demand for, bottled water, I could just ask Ryan, okay, at this price, how much bottled water would you purchase? At this price, how much bottled water would you purchase? And there, the demand just kind of shows up, right? But um, and honestly, for most of our analysis, and I would say probably like, I don't know, 70% of the analysis that economists do, that relationship where demand comes from on the consumer side, that's enough. We don't really need to like look underneath the hood, like what's going on in Ryan's brain when he's making these decisions um, of how much to purchase. So um, it would be okay. And I don't know if you've ever wondered this or if you're starting to wonder it now, but have you ever thought about like, how do I come up with those numbers? If Dr. Hunter asked me if bottled water is, 50 cents a bottle, and I estimate how much I would purchase in a week, where does that come from? Have you ever thought about that?
Uh, I mean, wouldn't it just come from, like, I guess the proper answer it would just come from whatever your utility for each unit of water is, but I guess you're just doing a quick assumption in your head on how much water you're going to need.
Yeah, but I guess the point is, had you ever like thought to yourself, well, like, gosh, like where do I get that information from? I mean, it's all intuitive, right? It's like
Yeah.
second nature. Um, and so the fact that economists have decided to come up with this utility theory and this consumer choice problem is a little bit mysterious. It should be, right? Because why do economists need, right, to explain the consumer choice problem? And that's kind of what I wanted to get to next. So so and the answer is um, something that only if you were really an astute observer of science in general would you get to. And that is, economists developed this consumer choice problem and analysis during the mid 20th century. So, from 1940 to, 1970, they developed all of these techniques. And the reason they did that was because, guess what? The law of demand isn't really a law. The law of demand says that demand curves should look like this green line and they should slope downward. Um, but sometimes demand curves slope upward. And there was a big crisis in economics because almost all of our analysis assumes the law of demand and the law of supply. And I don't know, Ryan, have you ever heard of something called, it's in physics, called the Universal Law of Gravitation?
Um, yes, but a
Yeah, you don't have to know the
long while ago.
Yeah. So it has to do with how much gravitational force exists between two different bodies of different masses based on their distance,
Hmm.
right? And it's the universal law of gravitation. So it's supposed to apply here on Earth and, out in the universe generally, like everywhere, right? The rotation of planets and um, solar systems and galaxies and all that other stuff. And the only reason why I bring it up is that if it turned out that the universal law of gravitation was shown by some data to be false, then everybody in physics would freak out, right?
Yeah, because everything they've built off would be false.
Yeah, like needs some serious modification anyway.
Mhm.
And without going into too many details, that's type of stuff has actually happened in physics, and that's why we have quantum theory and that deal with really, really tiny um, particles and stuff like that. I'm not a physicist. I am a science fan. So
Mhm.
I read about this stuff from time to time. But the main point is that in every science, if you end up with data that's inconsistent with your theory, which a lot of times get expressed in the form of laws. A law is supposed to be a special designation for a theory with a lot of support behind it. But it turns out in economics, the law of demand got destroyed because there were examples of demand curves um, sloping upward, and you could imagine I could probably sit here and talk to you and say, hey, listen, can you think of a good where if the price of the good goes up, people want to purchase more of it? Can you think of any examples?
Um, Not really. Uh,
Okay. Should we open it up? Can anybody else think of any examples? If anybody else wants, you can send a chat. You can say uh, vol for I volunteer. Okay. Okay. Well, we're not getting any volunteers, so I'll go back to you, Ryan. Um, what about Gucci?
oh, I suppose yeah, it could make the brand seem more premium if the
Right.
price is higher.
Yeah. So like that's one example of they're called network effects. That's the official label for them, and it includes things like what people call like a bandwagon effect, which is that, like you said, when something seems like it's exclusive, then it's more desirable,
Mhm.
and that can happen. But the most common example in economics, and the one that really inspired this, has to do with something called a Giffen good. And I don't know if you've heard about a Giffen good before or not.
No, I haven't.
Okay. So a Giffen good is a good that is an inferior good. Okay. And you know what an inferior good is? They're not, a Giffen good and inferior goods aren't the same thing. A Giffen good is a class of inferior goods. Do you remember what's going on with an inferior good?
A bit, tiny
Okay.
bit.
Yeah. So inferior goods are goods like a lot of times people say like generic products,
Okay,
right?
yeah.
And another example that people like to use is bus tickets, right? And for inferior goods, when your income goes down, then you want to purchase more of them.
Mhm.
Um, I'm putting that in the chat. Purchase more inferior goods. And so to contrast that, the label you're probably also familiar with, or you should be familiar with, is something called a normal good. A normal
Okay.
good is a good when your income increases, you want to buy more of it,
Yeah.
right? So, and they call it normal goods because that's what normally happens, right? If your income goes up, you want to purchase, more cell phones and more dishes and more of most foods that you like and more, stuff. Your demand increases. But for inferior goods, it's the opposite. Inferior goods are those goods that you only purchase because you can't afford something better. So, like the bus ticket examples, when your income goes up, you normally don't purchase more bus tickets, right? You buy a car,
Mhm.
right? So inferior goods are common, but Giffen goods are goods that we're going to talk about, but they're super inferior, which means that when income goes up for a Giffen good, people want to purchase a lot less of it, not just a little bit less, right? So
Yeah.
without getting into details, I'll say Giffen goods are super inferior. Well, it turns out that for super inferior goods, that it's easy to demonstrate that demand curves will slope upward. And because of that, the law of demand doesn't really apply to Giffen goods. So I'll say this law. So it's not really a law, right? It's like finding a place in the universe where the universal law of gravitation doesn't apply. so, so, so it can't be the universal law of gravitation, right? Because it sometimes doesn't apply. So
Yeah.
law of demand does not apply um, to Giffen goods in a lot of cases. And I'm just going to say it that way. It's kind of a weak statement. But so what economists did was just like quantum theorists in physics, they said, oh, we have this class of exceptions where the standard theory doesn't apply well. So we need to expand our theory. And the idea is to come up with a theory that's more robust, meaning that it can explain all the data that that is being observed. It can explain not only stuff happening on the very tiny quantum level, but also stuff on the gigantic, universal level. And and so this utility analysis, this consumer choice problem, actually is really important because it adds this caveat and enables us to explain what's going on with Giffen goods, and that's where we're going. Um, so um, so I'll just say this: law of demand only applies to normal goods, and that's what the utility analysis enables us to figure out. So it's really important to understand that we can move from the price expansion path to the demand curve, and that we're going through the trouble of adding this additional piece of theory because we want to, as economists, understand Giffen goods too. And we can't really understand Giffen goods and what happens with the demand for inferior goods without this utility analysis. So the hard part of what we're doing has a payoff. We're making things more complex. We're not just saying, okay, Ryan, at different prices, tell me how much you're going to buy, and we know you're going to obey the law of demand. We're saying, okay, we've got to look a little bit deeper into what's going on with Ryan in order to understand why, if I'm asking Ryan about a Giffen good, he might give me answers that um, don't obey the law of demand. So that's the big picture issue. Is that clear?
Yeah.
Okay. So I'm going to stop sharing and I'm going to go back to um, the whiteboard. Okay. All right. So um, one of the things that I want to do first, and we talked about this last time, and I don't know if everybody remembers or not, but um, I'm gonna go ahead and continue on as if you did. It's fine to go back and review the previous lectures, but we're going to have the quantity of y on this axis and the quantity of x on this axis. And now I'm just going to talk about the consumer's preferences. So we said, and oh, hold on, let me see if I can get this to draw properly. Okay. We said that the consumer actually has this three-dimensional utility function. You give the consumer a quantity of x and a quantity of y, and then we have the z-axis, and we'll plug that into our utility function. Our utility function is going to look something like this. We said, and utility is equal to some general function of the quantity of x and the quantity of y that the consumer chooses. Now, in our case, in most of our examples, we're going to limit ourselves to this Cobb-Douglas form for utility function, which is we'll take the quantity of x and we'll raise that to some power alpha or a, and then we'll multiply that by the quantity of y raised to some power beta or b. Okay. And we talked about that last time and how we could plot our three-dimensional function. But what we do is for our analysis, we construct these contour maps, and a contour map gives you a projection of all of the altitudes of the utility function in 3 dimensions. So, and these should be smooth, but I don't have the ability to control the pen, so they make smooth curves like we saw in the prior graph. But each one of these levels is a level of utility. So for example, U is equal to, let's say, 10. And so what this means is that for every consumption bundle on this locus of points, and we call it an indifference curve, and I'll okay. And so this is an example of an indifference curve, and this is another indifference curve, and this is another indifference curve. And all of them are associated with a different level of utility. So let's say U is equal to 8, and say U is equal to 5. So the only thing that we know, right, when we draw out these indifference curves is that there is a direction of increasing utility, which is, like I said before, it's the direction of getting more, right? Because we know the consumer is monotonic. So we know these indifference curves that are to the northeast are going to be associated with higher quantities of the goods, but that's all we know. We'll be getting to higher levels of utility as we move to the northeast. So we go from utility equals 5 to utility equal to 8, utility equals 10 in this example. And when you have a collection of indifference curves like this, we call them an indifference map because you have a set of them. Okay. And let's see, I will, so Hannah, are you with us this morning?
Can you hear me?
Yeah, I can hear you now.
My mic just wasn't working earlier.
Okay, so how are you doing?
I'm all right. How are
Okay, pretty good, pretty good. So is this making sense so far?
you? I mean, kind of.
Kind of, sort of, in a way. Well, I mean, you should be doing the reading too and all that stuff, but I'll give you a kind of a primer here. We'll talk a little bit. So on this indifference curve here, I'm going to indicate one consumption bundle. See the red dot? And there's another one here, another consumption bundle, if I can make it big enough. Can you see those two red dot consumption bundles?
Yeah.
So what I'm saying is I haven't given us a specific utility function because I have a form, but I didn't tell you what A is and I didn't tell you what B is. So like whatever, right? They're just numbers. And the only thing that we know is that A plus
Not
B.
x raised to the a?
What's that?
Not x raised to the a times?
Yeah. So it's X raised to the A power.
Yeah.
Yeah. So, but you don't know what A and B are. But there's some numbers like we talked about last time. It's like, 1/2 and 1/2. A and B have to add to 1.
Mm-hmm.
But so if I pick, let's say this consumption bundle here, all I know is that if I have whatever the quantity of X is that's associated with that and the quantity of Y, and I plug them into this function, I'll get 5,
Mm-hmm.
right? Likewise for this one. If I plug in,
5 both times?
yeah, I would get, so, yeah, let's see. I mean, I don't know if it's clear. I'm gonna try to do this, but let's say for this one, Y is equal to, I don't know, 7,
Mm-hmm.
and X is equal to 3, right? So it's clear like what the location is that I'm talking about, right?
Yeah.
And so with this consumption bundle here, it's associated with 7 units of Y and 3 units of X. So if I don't know the form of this function yet, right? I could, come up with an example, but we'll just play along, right? So if I put, for X, I put 3 raised to the alpha power times 7 raised to this beta power,
Mm-hmm.
then I would get a number out, and that number would be 5.
Mm-hmm.
And likewise, with this one, the quantities are going to be different, right? X is like, I don't know, 6, and Y is like 4 or something like that. But I put those in here, and I also get 5. And that's why they're on the same indifference curve. Do you see what I'm saying?
Yes, that makes more sense.
Yeah. And so I don't know if you're familiar with the and I think I misspelled it anyway. There should be 2 F's here, but it's okay. It's not English class. But I don't know if you're familiar with this expression, indifference. You know, sometimes if people say, would you prefer, a hot dog or a piece of pizza? And you say, I'm indifferent, right?
Yeah.
What does that mean to you?
Well, if it's using it in that context, then it means like you don't really know.
Ah,
You're indecisive.
okay.
You
Or
don't really want either of them.
no. So indifferent means that you don't care. I'll take either one. I don't know if you ever sit down with your family and eat dinner. I hope you do. And I don't know if you guys sit around and try to figure out what to have. And I don't know if anybody in your family is easygoing, but I really, for me and like one of my daughters, we're really flexible. We're like, meh, want to have pizza tonight, want to have Chinese food, want to have whatever, like we don't care, right?
Mhm.
And that means we're indifferent between those options. We really don't care. We rank them all the same. I'll be just as happy with pizza as I would be with Chinese food, just as
Mhm.
happy. And that's why we call these indifference curves, because the idea is that whether
It doesn't
I'm,
matter where you are on the curve, you're still
yeah,
gonna get.
whether I'm here or here or here, any of these combinations of X and Y give me exactly the same amount of utility. I'm fine. And so actually we call them indifference curves, but I like to call them, and a lot of times you'll see that they just use the abbreviation IC, I and C, like that. And so I like to call them I don't care curves, because that's really what it means. I don't care. Give me that. Give me this. It's all going to give me the same amount of utility. I don't care. All these options are the same. Okay. Does that make sense?
Yeah.
But if I was to be offered a choice between, let's do a different color. If I was to be offered a choice between one of these options, so see the pink consumption bundle. I don't know if it's clear enough that that's pink.
Yeah.
But if you ask me, would I rather have this one or that one? Well, then I know, because it's on a higher indifference curve. It gives me more utility. So I would prefer the pink one over either of these red options. That makes sense?
Yeah.
Yeah. So this is just one way of representing a consumer's preferences, and the one that we use most often in economics. And again, what we're doing is we're plotting their utility function in 2 dimensions. And so that's a little bit strange. I don't know if you've ever seen have you seen these types of contour maps before? Sometimes they're called level curve maps, and they use them in calculus, but there's another.
Oh yeah. I just took Calc 3.
Yeah. So you've seen level curve maps then.
Yeah.
Yeah. So this is exactly what we're doing, is we have these level curve maps, and we're plotting this 3-dimensional function in 2 dimensions.
Mhm.
And yeah, to get the shape of the level curves. And the assumption is that the consumer is, and I said this last time, but I'll say it again, is that the consumer's objective is to maximize, get the highest level utility. So the consumer always wants to get as much utility as they can. And here, all we know is that they would try to get on the highest indifference curve that they could. But in order to really make it a choice, we have to introduce, again, the notion of affordability. So we put those indifference curves together with the budget constraint that we had before, the budget line. So I'm going to draw the budget line, and then I'm going to draw a set of indifference curves. And so here's one indifference curve, and here's another indifference curve. And again, they're supposed to be smooth, but I'm not really good at drawing on my trackpad. So, and then I'm going to draw another one. Okay. And I'm going to highlight this point here, which is supposed to be a point of tangency between the budget line and the indifference curve. And it's like we saw in the textbook. The idea is if these represent the consumer's indifference curves based on their utility function, then the budget line tells us, again, what's affordable and what's not affordable. And what we know is that, for example, since the consumer is monotonic, we know they're always going to be trying to get more of both goods. But if we were to, for example, say, well, maybe, so we know the consumer is going to consume at some point on their budget line. And so consider the two green points. See these 2 points, Hannah?
Yeah.
And we can say, well, those are possible points, right, for the consumer to consume at. But would the consumer choose either of these points? Well, for one thing, they'd be indifferent between them, right? They wouldn't care. They're on the same indifference curve, right?
Yeah.
But there's this other point that's on a higher indifference curve, so it's associated with more utility, that's also affordable. So what our ultimate solution to the consumer choice problem is, and I'm going to go ahead and I'll label this in orange. I'm going to call it Y star, and X star. That's the address or the quantities of goods X and Y that are in the orange consumption bundle. Can you see that? So that gives me Y star Y and X star X. That's the consumer's optimal consumption bundle. It's the one that maximizes their utility. But you'll notice something kind of, well, I mean, hopefully you think it's interesting. But in terms of identifying it, right, it happens at this point of tangency between the budget line and the indifference curve. Do you see what I mean?
Yes, I'm listening.
Yeah. So that's how economists end up solving the consumer choice problem. And I want to draw one other, or make one other analogy here really quickly and see if you get this. This is a simultaneous equation problem, very similar to the demand and supply problem, right? There's demand and here's supply, right? And the equilibrium that we see happens at a point of intersection between these two linear equations. And by the way, demand and supply don't have to be linear, but it's at a point of intersection, right?
Mm-hmm.
So that's pretty similar, right? I mean, the difference is that this is a point of tangency, and technically the difference between tangency and intersection is it's still just one point, right? But in the intersection example, the two equations are being satisfied simultaneously and they're crossing one another. And here, right, you've got a point that's identified as satisfying both this indifference curve equation, which we don't know yet, and the budget line, which is another equation. And it's a single point where they touch. It satisfies both of the equations, but they don't cross each other. But you see how it's very similar, right?
Yeah.
So we're gonna, use that analogy to help us work out the mathematical solution that will identify this point of tangency. So, okay, let's go ahead and look at the consumer's choice problem from just the math. Okay, so we want to maximize utility, and this is called a constrained optimization problem. Again, if y'all have had calculus, then you probably have seen this sort of thing. And it's generally, in our case, we're going to confine ourselves to a particular type of utility function, which is this Cobb-Douglas x to the alpha, and I'll try to be a little bit more explicit here, times y raised to the beta power, right? And then we say it's going to be subject to the budget constraint, which is, and now I'm going to switch to using income. I is equal to the price of X times the quantity of X plus the price of Y times the quantity of Y. Okay. So this budget constraint equation we already showed is our budget line. It's just, this is the equation in general form. We solve it for y to get the slope-intercept form. And the utility function is going to give us our indifference curve map, okay? And so what are the two equations? Well, we know one of them is going to be our budget constraint. The other one is a little bit more challenging to articulate. It's where the slope of this indifference curve, right, is equal to the slope, because that describes tangency, equal to the slope of the budget line. So the two equations that we're going to use, and I call them conditions, okay? So the solution to the consumer's utility maximization problem, and I'll go ahead and this is the consumer's utility maximization problem here. Has two conditions that must be satisfied. And okay. So condition one, I call the tangency condition. And the tangency condition in words says the slope of the indifference curve that represents the consumer's highest level of utility is equal to the slope of the consumer's budget constraint or budget line. Okay, Hannah, does that make sense?
Yeah.
Okay, and I just call that the tangency condition. And mathematically, it looks like this. The slope of the indifference curve, okay, the slope of the IC has a name. It's called the marginal rate of substitution, or we can just call it what we normally use for shorthand, the MRS. Okay. And the slope of the budget constraint is, and we saw this before, it's going to be minus px over py. Now, everything that I've said here is almost true, okay? Because technically speaking, and I don't know if you can see this or not, Hannah, but check it out, right? So here's the budget line, and you can see it's a downward sloping line, right? Are you with me?
Sorry, I was muted. Yeah.
Yeah. See, it's a downward sloping line, right? So notice, right? X is a positive price and Y is a positive price. So we say it's minus px py because downward sloping lines have negative slopes, right?
Mm-hmm.
But and this is nonlinear, so the slope is changing. But notice along the indifference curve, the slope is everywhere negative, right?
Yeah.
So that means that this expression, the MRS, would be negative too if it was the slope of the indifference curve, right? It should be a negative number too, because they're both downward sloping. Does that make sense?
Yeah.
But actually, the true, right? The actual relationship here is, and let me see if I can get my highlighters over here. The truth is, and okay, the slope of the indifference curve is negative. The marginal rate of substitution is actually, and well, maybe I'll write it this way because you won't be able to see, is the absolute value of the slope. So the marginal rate of substitution is not actually the slope of the indifference curve. That's the point that I'm trying to make. It's actually the absolute value of this slope, okay?
Mm-hmm.
And since we're going to be using absolute value for both of them, we don't need this negative sign either. So our condition, you know, they could either both be negative or they could both be positive, but you can't have one be negative and one be positive because they're not going to be equal, right? So ultimately our condition is going to be as follows. And honestly, it depends on the textbook, right? But we're going to end up with the condition, the tangency condition is the marginal rate of substitution is equal to px divided by py. We get rid of the negative here and we throw away the negative there. Or we could say, if we wanted to be, you know, more exactly descriptive of what's on the graph, we could say that the IC slope is equal to minus px over py. Do you see what I'm saying, Hannah?
Yes.
Yeah. But this is the way that the tangency condition will normally be expressed. Okay. So, and then our second condition is just what I call the budget exhaustion condition. And that just means that the consumer uses all of their budget. The point is on their budget line. So to kind of summarize this, I'll boil it down. The two equations / conditions that must be satisfied to find the consumer's optimal, and optimal just means best, which means in our case maximizing utility, the consumer's optimal consumption bundle. Okay. And I'm just gonna write simply the tangency condition, which is MRS is equal to PX over PY. And the budget condition, which is I is equal to PX times X plus PY times Y. Okay. So okay, Hannah, I got another question for you. Are you with me?
Yeah.
So this is kind of the summary of everything that we talked about here. Okay.
Yeah, I gotcha.
So just to kind of put it all in one place in a simple way without any caveats, you know, this is what we're actually going to be working with. But do you notice how this is similar to, right, the equilibrium for a competitive market? The only difference is, right, there we have simultaneous equations, right? So market equilibrium, and in that case, right, it's supply, and we could have equations, right, like we did before. PV is equal to C plus DQV. Does that look familiar?
Yeah.
And demand, which is PB, is equal to A minus B times QB, right? And we find out in equilibrium that it's the same price and the same quantity, so we can get rid of these little subscripts. But it's just two equations in two unknowns. We don't know P and we don't know Q. And here, we don't know X. And we don't know Y. And it's not clear where X and Y are coming from here, right?
Mhm.
But you see, it's just two equations in two unknowns. And I'll do one other thing that's you guys are going to find out in just a minute anyway, just to kind of hammer this home. And that is, so I'm gonna see if I can select this. Let's see if it'll let me grab it all. It's not gonna let me. Okay, so I'll just get rid of this one. And I'll say, so for our main example, Cobb-Douglas utility, one, the MRS is AY over BX is equal to PX over PY. And our second equation, we already know. I is equal to PX times X plus PY times Y. Okay. So I don't know if now you can see, but these are two equations, Hannah, right?
Yeah.
And we're going to solve them for Y and X. Those are our two unknowns. So the only kind of like subtlety here is we have to figure out, well, okay, how should we plug things in? And in this particular case, I think now it's better to start with an example. So, okay, we'll do a consumer optimization problem. And so let's maximize utility, and we'll say it's going to be like we did before, X raised to the 0.5 power times Y raised to the 0.5 power, subject to the budget constraint, which will say the person has $100, and we'll say the price of X is $2. So we'll have 2X plus the price of Y. Do you want to pick a price for Y, Hannah?
25.
It's gonna be expensive. How about we make it 20?
Sure.
Or I suppose I won't be a spoil sport. We'll do 25. Maybe that's that. I mean, it's fine. It doesn't matter.
Whatever's easiest.
That's fine. So we could go ahead and we could graph the budget constraint and stuff like that. But let's go ahead next and say, so, and this actually confuses a lot of students, and their questions worded this way on Ignithium. You're given this information, and then you're asked the question, how much X will the consumer purchase? And that's just asking translation, what is X star? So those are the same questions. Does that make sense, Hannah?
Yes.
It's the same question, and that confuses students a lot of times because they get used to kind of asking or thinking about things in the purely like technical sense. They solve for X star and they don't know that that's a prediction of how much the consumer is going to purchase. So you know, it's always worth keeping in mind that we're actually trying to get down to something in the real world, which is if you got $100 to spend and you know, I don't know, Red Bull is $2 a can, and filet mignon is $25 a piece at the restaurant, right? What are you going to do if these are your preferences? How much Red Bull are you going to purchase, and how many filet mignon, nice steak? How much steak are you going to buy, right? So this question is just asking about one piece of the consumer's optimal consumption bundle, which is how much X they'll purchase. But when we do the solution, we'll also get a Y star also, which depending upon the question, we might want to know that too. So if we use our two conditions, I'll go back here, right? So our marginal rate of substitution is going to be alpha y over beta x, which is a little bit sort of counterintuitive, right? Because we said this is x to the a and y to the b, right? And over here, you kind of end up with it reversed, right? Y ends up associated with a and x ends up associated with b. And I haven't worked out the math to explain that yet. And it's just something that at this point in time you should memorize and keep track of. It's not that I don't intend to explain it. I will, but we'll probably do that next time. So I'll ask everybody and let you guys have a minute. We have about 15 minutes left to go ahead and use these two conditions and the information we have here and work on finding X star and Y star. And then I'll come back in about 5 minutes and help you all talk about the solution. So
wait, did you say you want us to find X star?
Yeah. Yeah. Well, I mean, you'll find Y star too. So you have to find X star and Y star. And let's see. So Diego, are you here?
Yeah, I'm here.
Okay. So I'm gonna ask you in about 5 minutes. And Marlena, are you here?
Yes, I'm here.
Yeah, and I'll ask you in about 5 minutes too. And how about Emily? You here? Emily Cobian? Are you there, Emily?
Yeah, I'm here.
Okay, so I'm going to ask you in about 5 minutes too. All right. So there's the information. You can write it down and try to do that with it and solve them. Does anybody, since I don't have it on the exact same screen, it's better to write this problem down. Yeah, and then I'll leave you guys with that. Okay? Okay. All right. So I'll see you guys in 5 minutes. Okay, I'm back. So I'll do the chat. And so go ahead and put in the chat for our three leaders, Diego, Marlena, and Emily. Go ahead and put what you got for X star in the chat. Are you there, Diego? Can you hear me?
Yeah, I'm here. I'm just trying to work this out really quick because I tried to do this off of nickname earlier.
Yeah.
Where I'm not understanding the question, especially with the numbers that you gave us on the earlier screenshot.
Okay, well, let's try to walk through it a little bit, right?
Yeah, because I understand like the base concept.
So we have A and B, right? Which based on this, we both know are 0.5 and 0.5, right?
Mm-hmm.
And we have price of X, which is 2, and price of Y, which is 25, right?
Mm-hmm.
So we should be able to do this part, go like this.
Yeah, no, I got 0.08 or no, not 0.
Well, this should yeah, so this should just be right. We can go through the steps, but 0, and we can write it like this just to be a little bit more clear. 0.5. See, if you don't do the steps, you don't kind of like do it slow, then
I did it backwards. That's why I did it in 2 over 25 because that's how I thought it was X over Y, not Y over X.
Yeah, that's why it's important to have the formulas right. And then price of X over price of Y, right?
Mm-hmm.
So I don't know if you agree. I'm going to kind of stretch this out, so hopefully you can see it all in one line, right?
Right, I can see it.
We're good.
Mm-hmm.
And
yeah, that's what I was saying before. 2 over 25.
Yeah. So this, since the 0.5 over 0.5, those cancel, right? We could rewrite this as Y is equal to, and I'll try to be more explicit, times X, right?
Right.
Okay. And so then I don't know if you kind of are comfortable with the whole approach to simultaneous equations, but like in basic demand and supply, what we do is called substitution and elimination. You find there you're dealing with price and quantity as the variables, but in general it's just X and Y. And so you normally find take one of the equations and write one of the variables in terms of the other, and then you substitute it into the other equation. You see what I mean?
Mm-hmm.
And so down here, I'll just start a new line. And so we have 100. This is just what we had before, right? 2x plus 25y, right? And now we're going to plug in for our y. So we'll have 100 is equal to 2x plus 25. And then we write in what we had for y, which is 2 divided by 25 times x, right?
Mm-hmm.
And I could be a little bit like more careful with the parentheses, just so we don't cause any confusion. If I was writing this on a board in class, you'd be able to see, but that's what we have, right?
Mm-hmm.
And then you can see like the 25 and the 25 should cancel, right? Because it's 25 times 2 divided by 25, right? Do you agree?
Yeah, I'm following.
And so I can simplify that by just saying it's 100 is equal to 2x plus 2x. And so we have 100 is equal to 4x. So you see, once I do the substitution, I end up with one equation and one unknown, right?
Yeah.
And then this would be our x star is equal to 25. And right. So so I ask Marlena and Emily, is this what you got?
Yes, that's what I got.
Yeah.
Yeah. And so does it make sense, like our technique?
Yes.
Yeah, it does.
So
Yeah.
you're just figuring out x. You're not doing anything with y then. I mean, like obviously you're getting the.
Well, check this out, right?
Oh, okay.
So now that I solved one of them, I just
Mhm.
put that back in there, and I have and I can change this, right? And then I would have my y star.
All right.
Do you see what I mean? That's
Yeah, I see what you did there.
That's the whole flow. Substitute and eliminate, or eliminate and substitute. Here, this depends, again, this is language I'm using from 9th grade, 8th grade algebra.
No, yeah, I understand that. It's just
You
the
know.
last time I did this function, I did it in macro, and I thought there was like a lot more to it. So I was probably just overthinking it. Because I thought there was like 2 more variables I had to worry about, and that's why I was kind of thrown off.
Well, to be clear about it, I mean, in macro, they use Cobb-Douglas production functions.
Mm-hmm.
And I don't know if it's common to use Cobb-Douglas utility or not, but you might have been confused because a lot of times in macro, they'll use a Cobb-Douglas production function for labor and capital, and then they'll have a technology parameter, which is an additional thing.
Mm-hmm.
And we're not using that right now. We're just using the simplest version of a Cobb-Douglas utility function. Remember, the whole Cobb-Douglas bit is this. It's just this functional form. The x raised to the alpha times y raised to the beta. That's just, an equation form. And you could use it for utility, or you could use it for production, or you could use it for anything. It's just like, an equation for a line can represent anything, right? Anything that's a line. It could be a line for demand, or a line for supply, or a line for, I don't know if you're familiar with, if you remember from macro, the Phillips curve.
Yeah, I remember that one.
But a lot of times those things look linear. So people use a linear equation to describe them. So Cobb-Douglas is just a functional form. So here we're using it to describe the consumer's utility. And then we, in one of the equations, right, write the equation so that one variable is explicitly in terms of the other one. And then we substitute it into the other equation. So we've eliminated one of the variables. In this case, we eliminated y from the equation. And now we just have one equation in terms of x. And then we find x. And then you can, once you've eliminated it, you can substitute it back into the other equation in order to find both x star and y star. So in this case, so Marlena, you want to tell us, did you get y star?
For y star, I got 2.
Yeah. So you see, Diego, you just put the 25 in there, and then it's 2 over 25, and again the 25 cancels, and you just end up with y star is equal to 2.
Cool.
So this is kind of like the simplest kind of example that we could do, and you all know that there are other examples on Ignithium, and you can do as many as you want to, but this is the technique that you would use. And what we ended up finding is we ended up finding this X star, Y star, this tangency point. That's what we found. Okay. Now, I will tell you one other thing. It's also asked on a Nithium that you guys can play around with until next time, which is now that we have X star and Y star, we know it's X star is going to be 25 and Y star is going to be equal to 2. We can substitute X star and Y star back into the utility function to find our level of utility that we achieve, our U star. Okay. Emily, does that make sense?
Yeah, that does.
And then we could label this indifference curve with a label U star, and we would have a number like we did before. In these cases, we knew U is equal to 8 and U is equal to 10. Now we would know what U is associated with all of these different consumption bundles that lie on this indifference curve that represents the consumer's highest affordable level of utility. Okay, so I think we did quite a lot today. Does anybody have any questions for me? No. Okay, everyone. Well, good job. And we'll pick this up next time. So now, just to put it out there, you should be able to solve all of the questions on the consumer choice homework, with the exception of, I think, the last 2, which have to do with the substitution and income effect. And we'll talk about those next time and work on this a little bit more. But if you're thinking ahead, from this point forward, you should think that the consumer choice homework is probably going to be due in about 10 days. So maybe like Tuesday after next Thursday. And then pretty soon, like another week after that, we'll be ready for our second assessment, which will be on this material. Okay. So
Assessment will only be on this section.
oh yeah,
Okay.
we have exactly 3 sections: supply and demand review. I mean, this class is really like 3 midterms.
Mhm.
And I should tell you that it's really common for people to do like their highest score to be on the next thing, which is the consumer choice problem, and their lowest one, the last section we're going to do, which is on supply issues. So anyway, if this stuff sounds pretty good to you, try to nail this exam, because it's the one that most people do really well on. So that should kind of, give you some encouragement. And then we'll move on from there. Okay. All right, everybody. Again, take care.